Satellite dishes, both large and small, are being installed around the world at amazing rates that will only accelerate as time goes on. Whatever the size, the difference between excellent satellite dish reception or poor signal quality often boils down to one thing: the installation. Thousands of well-trained installers will be needed to install millions of dishes worldwide in the years ahead. A correct installation performed by a skilled installer can pull out that last fraction of a decibel in signal strength, making the difference between problematic reception and a perfect TV picture. But what is it that makes an installation picture perfect? It's not as simple as it may first appear. There are a lot of little things that can go wrong, and numerous details to which the professional installer must pay attention. What's more, the ongoing evolution of satellite use, from traditional analog television to digitally compressed MPEG video and high-definition TV, plus two-way data communications, continues to place new challenges before even the most experienced satellite technicians and installers. To explain all the technical ins and outs of satellite dish installations, we turn to Mark Long, an internationally recognized authority on satellite communications who has been installing, operating, and maintaining satellite TV receiving systems all over the world for over 25 years.
Satellite signals are microwaves which travel in a straight path along the line of sight, and all geostationary satellites are located in an arc that goes across the sky. If we want to receive these satellites, we need to have an unobstructed view of this arc. You can conduct a preliminary survey at the site by facing south for locations north of the equator or north for locations in the southern hemisphere. Here we have a relatively clear and unobstructed view of the sky from the southeast to the southwest. Even at this site, however, there are limitations. The mountain blocks our view of the southwestern horizon, and trees block the southeastern horizon. To determine which satellites may be blocked from any given location, we will need to learn the two basic coordinates for finding any satellite: the azimuth and the elevation. The azimuth coordinate represents the bearing of the satellite from the site location, while the elevation is the tilt angle at which the dish looks up at the satellite. Every satellite within view from the site location has its own unique pair of azimuth and elevation coordinates, which can be calculated using a computer program or a simple as-L chart. One of the ways to get information about satellite signal levels or to calculate azimuth and elevation angles is to go to the internet. Once you know the azimuth coordinate for any satellite, you can use a compass to determine its direction from the site location. To achieve a high degree of accuracy, however, you must first correct the compass readings from magnetic north to true north. Magnetic correction maps are available for different regions from a variety of sources. Or you can call up your local airport control tower to find out the correction factor for your area. If true north is east of magnetic north, the correction factor must be subtracted from the compass readings. When true north is west of magnetic north, the correction factor is added. All compass readings should be taken out in the open, well away from large metal objects or overhead AC power lines and transformers. In the northern hemisphere, the satellite nearest to true south, that is 180 degrees from true north, will have the highest value of elevation. When we say elevation, we mean the angle in degrees at which the dish must tilt up from the horizon in order to receive the satellite. For locations south of the equator, the satellite nearest to true north will be the highest in the sky. The further away the satellite's direction or azimuth bearing is from the site's true north-south line, the lower its elevation in the sky. An inclinometer is another tool that we use to determine the elevation angle that is required to see the satellite. Once we know the azimuth and elevation coordinates for every available satellite, we can point the inclinometer in the direction of the corrected compass bearing and then tilt it back until it reads out the satellite's elevation angle. We therefore can visually confirm whether or not any satellite will be available before we even begin constructing the dish. If trees, terrain, or buildings block the view, then we can consider another, more advantageous location nearby. Terrestrial interference from land-based telephone transmitting stations or airport, shipyard, and military radar installations also can restrict or even preclude satellite reception. This particular site is between two telephone links, and this affects our reception of certain satellite TV channels. The spectrum analyzer displays the interference source when the LNB is pointed in the direction of our local microwave telephone relay station. At this location, the interfering signal consists of just a single narrowband channel. In some cases, this interference can be removed by using a special narrowband filter built into the receiver. In other cases, however, the interference may be much more pervasive, with strong, multiple interfering carriers. It's always a good idea to sweep any prospective site with a spectrum analyzer before attempting an install. That way you have advance warning of any potential TI problems and can select the exact spot which will experience the least amount of interference. The interference will appear on the analyzer's display as a spike sticking up from the noise floor. Some installers prefer to use a portable test antenna and spectrum analyzer to confirm signal strength and availability before installing the dish. Others prefer to rely on the available satellite coverage maps to determine the satellite signal strength at the site location. Larger dishes require a concrete pad as a supporting foundation for the mount. It's best to pour the pad the day before you intend to begin installing the dish, so it has time to cure. Be sure to pour the amount of concrete recommended by the manufacturer into a form that extends well below the local frost line. If the antenna mounts onto a pole, be sure that the pole has a crossbar at the ground end of the pipe to keep it from rotating after the cement hardens. Check to ensure that the pole is supported in a straight up and down or plumb position. For rooftop installations, you will need to be sure that the building structure is capable of supporting the weight of the dish as well as withstand the uplift forces of several thousand kilograms, resulting from moderate to high-speed winds. Consult your local building ordinances to ensure that you comply with all their requirements. The satellite dish should come with a detailed set of instructions covering all the essential construction information. When you first receive the dish, check to see that all parts listed in the manual are present and accounted for. Read over the instructions to see what tools and other materials will be required. On the evening prior to assembly, check the local weather forecast to ensure that your efforts will not be interrupted by rain or heavy winds. Begin assembly early in the day to allow enough time to complete the project. Solid petalized antennas are best assembled face down on a flat surface such as a concrete driveway or outdoor patio, while mesh antennas should be assembled face up to prevent damage to the mesh material. If assistance during assembly is recommended, arrange to have a friend or two available to help lift the dish onto the mount following assembly. In order to obtain the maximum performance from any satellite dish, it is necessary that the surface precisely conform to the parabolic curve selected by the antenna engineer who designed the system. Any noticeable bumps or waves in the surface can lessen the amount of signal arriving at the focal point of the antenna. You can tell whether an antenna has the necessary accuracy by running your hand along the surface and feeling for any noticeable bumps or waves. A visual inspection will also tell you a lot about whether the screen has been attached properly. Many mesh antennas use a series of clips in order to hold the mesh onto the frame of the antenna. These clips must be attached to the frame at regular intervals in such a way that there are no noticeable bumps or waves in the surface accuracy. Care taken by the installer when putting the mesh onto the frame will be rewarded with the best reception possible. Many solid metal and fiberglass antennas are constructed from a series of petals which fit together to make the dish. The installer should take care that there is little variation from petal to petal. Once assembled, you can check a dish like this for surface inaccuracies by running a series of strings across the center at evenly spaced intervals. The strings should all lightly touch in the center. Gaps of 1/16 of an inch or more indicate that the antenna's room is not a perfect parabola. On this particular dish, these strings indicate that those petals are too low. The two edges should line up parallel to each other. If it doesn't, you may have to loosen some of the bolts and retighten them in a way that reconforms the antenna shape.
One of the more interesting things about satellite antennas is that they don't always work exactly the way the manufacturer intended for them to work when you take them out of the box. The trick is the feed. We'll look at why the feed itself, it can be misadjusted and cost you many precious dB in signal. The secret of the proper performance of an antenna is found right here. It's a circle. It's a circle with a hole in it, a little piece of plastic that covers the hole to keep the moisture out. All of the satellite energy that collects on the satellite reflector itself collects down here in the reflector and returns to this spot or some spot like this within this opening. It's your job as an installer to make sure that this whole assembly, this outer ring and the hole in the center, are positioned exactly in the one spot where all of the energy from the satellite dish will focus and then collect. Since this portion must be exactly in the center of the whole surface, you have a rotation mechanism this way. Two Allen set screws in this particular Odom series dish release, and then this whole mechanism rotates left and right. Again, what you're trying to do is to find the exact precise center where all of the energy is focused by the surface itself. The other important adjustment on any satellite dish is found at some point in the center of the dish, the point where the feed support structure here is actually mounted. On this particular Odom dish, we have, again, a couple of Allen set screws that are up here in this corner. And as they're loosened, this whole mechanism will slide in and out to set the distance from this dish surface back to the focal point on the dish itself. Very, very important that everything you do with a dish be done precisely and be done with the proper instrumentation. When you take the extra effort to get the extra signal that is possible with any satellite dish antenna, you're more apt to have a satisfied and happy customer and to greatly reduce your own service calls.
Molecular motion in all matter generates a noise background which permeates the entire electromagnetic spectrum used to propagate communication signals, including the satellite frequency bands. Geostationary satellites, which uplink and downlink signals across a vast distance of more than 22,300 miles, generate enough power to overcome this natural phenomenon, but only when the correct antenna size and electronics are used to receive their signals. The temperature of all thermal noise is expressed in degrees Kelvin, a measurement scale that can be related to more familiar temperature scales, such as Celsius or Fahrenheit. The higher the noise temperature, the stronger the noise force. Externally generated noise is received by the parabolic antenna along with the desired signal. When the satellite dish tilts up toward the cold sky, its temperature is relatively low. If the antenna must tilt downward to receive a low elevation satellite, the antenna's noise temperature will increase dramatically because it is now able to see the hot noise temperature of the Earth. The actual amount of noise increase in this case is a function of antenna diameter. Minimum antenna elevation angles of 5 degrees for C-band and 10 degrees for Ku band are recommended. Thermal noise also is generated internally in the LNB's first stage of electronic amplification. C-band LNBs are graded according to their noise temperature performance in degrees Kelvin, while Ku band LNBs are rated according to an equivalent scale in dBK. In either case, the lower the LNB's noise rating, the better its performance. The noise temperature of our system also will increase if moisture is allowed to enter any of the system's connections. In some cases, moisture can cause irreparable damage if it is allowed to enter the LNB's internal electronic circuitry. Another potential source of damage to the LNB is lightning. Be sure that you connect the dish to a ground rod pounded into the earth next to the pad. Surge protectors also are available to protect the indoor electronics from damage. The first thing to notice on the Feedhorn is that the axis of the feed is aligned with the polar axis of the antenna. The servo motor, which rotates the probe inside the Feedhorn, has a 3-wire connection, which supplies 5 volts DC, pulse, and ground. When assembling the LNB and Feedhorn, make sure that the neoprene gasket that goes between the Feedhorn's flange and the mouth of the LNB is seated properly in the groove provided. Make sure that you use each and every one of the bolts provided by the feed manufacturer. Be sure that these are tightened, and in climates where there's a lot of rain, you can even seal the outer portion of this flange with a sealing compound such as silicone sealer. Otherwise, moisture may seep through this opening and disrupt reception. Some manufacturers combine the LNB and Feedhorn into a single seamless product called an LNF, short for low noise feed. This eliminates a potential point of moisture entry. If the LNF malfunctions, however, or if the owner later wants to upgrade to a lower noise temperature LNB, the entire product must be replaced. Most large dishes are actually symmetrical prime focus parabolic antennas. The parabolic curve incorporated into the dish design has the property of reflecting all signals arriving along the antenna's axis of symmetry to a focus located to the front and center of the dish, hence the term prime focus. Check to ensure that the feed horn is centered over the dish. You can do this by taking 4 measurements at equidistant points from the feed horn to the rim. All of these measurements should be equal. Another measurement that will vary from antenna to antenna is the focal distance. That is, the distance from the center of the dish to the lip of the feed horn. This is specified in your antenna installation manual. The focal distance from dish center to feed horn opening is a function of the antenna diameter and the depth of the selected parabolic curve. If you need to calculate this distance on your own, run a string across the face of the antenna and measure the antenna's depth. That is the distance from the string to the face of the dish center. Focal distance can be calculated by plugging the dish depth and antenna diameter values into either of the following formulas. Once your system is up and running, fine-tune the focal length by moving the feed in and out in small increments while watching the readout of a signal strength meter or a spectrum analyzer. Another thing to check, put the inclinometer along the face of the feed horn and then across the back plate of the dish. These angles should be the same. Many feed horns for prime focus antennas can be divided into 2 parts. One is a scalar ring plate, which can be adjusted up and down the throat of the feed horn to match the focal length to antenna diameter ratio of the dish. To determine the F to D ratio of the dish, simply divide the focal length by the antenna diameter. The waveguide of an adjustable feed horn is marked with a scale that indicates the various F to D ratio settings. The F to D for a deep dish is between 0.25 to 0.32. Medium depth dishes from 0.33 to 0.39, and shallow dishes from 0.4 to 0.45. Adjusting the feed horn to the correct F to D value sets the feed horn's illumination taper. Under illumination of the dish will result in a loss of some signal amplification that the antenna would otherwise provide. Over illumination causes the feed horn to look over the rim of the dish and see the hot noise source of the ground below. If the feed horn that you use does not have an adjustable ring plate, be sure that the feed horn's F to D rating matches the antenna's F to D specification.
This is a C-band only horn. It has a servo motor on the back. It controls the probe inside to match the polarization of the satellite. And when you install this in the dish, you install it at about a 45-degree angle, and then the probe will go to horizontal and vertical. And when the satellite dish is properly tracked, you will find that when you're looking at vertical polarization, the little probe inside will be exactly parallel to the polar axis of the dish. And when you're looking at horizontal signals, it will be across the axis of the dish. There are other combinations of feeds that you will want. Of course, circular and linear combined. This is what we call a co-rotor, and it has in it a dielectric plate that makes it possible for you to receive vertical, horizontal, left-hand circular, and right-hand circular, all under the control of the satellite receiver. Also in the middle of this one, this is called a co-rotor, it has a 12 gigahertz feed, a K-band feed. I've seen many feeds, particularly on tripods or quadrupods where the feed is squinted off, looking not at the center. If it doesn't look at the center, the main beam will be asymmetrical, and the side lobes on one side will be very high and they'll be very low on the other. So it's important in this initial installation to get that precision. Make it look straight at the center. And when you do that, spend a little time to move the feed in and out to get the best focal point.
What this is called a focal finder. Stretch it out to that appropriate distance. Attach it to the front of the feed and see both, is this pointing to the center, touching actually the very center of the dish, or is it skewed a little bit? And we've been using here our little laser. We didn't really get this for our presentation, although it's been working very well for that. We actually got this. This is actually a tool that's used to mount onto the feed, and then it's sitting out there, and then you click it, and you see where does that dot end up. Is it ending up in the center of the dish?
This particular antenna uses a quad support for the feed. That is 4 separate brackets which position the feed horn over the front and center of the dish. Other types of antennas use a button hook feed. The advantage of this particular type of feed support is its strong rigidity. It holds the feed horn in place, whereas a button hook feed may move around in the wind. In addition to the coaxial cable, 2 additional cables are needed to connect the dish to the indoor receiver. The first cable supplies the motor with DC volts and a pulse count so that it knows how far to travel from satellite to satellite. The second cable provides the 5 volts DC pulse and ground required by the feed horn. All of these wires are contained in a single high-quality direct variable cable. Make sure that you purchase enough cable to complete the run all the way from the antenna to the indoor receiver. This may involve going down a pole, into the ground, up a wall, through an attic, and down an interior wall, while leaving enough left over to easily reach the back of the receiver. Here, we have connectors in the line because we are continually testing new products. For your installations, however, you should try to avoid any connections in the line because they are potential entry points for moisture. A shielded wire cable called coax is used to connect the LNB to the receiver. Coax is made up of an inner wire covered with a plastic or foam sheath and an outer mesh that is in turn surrounded by an outer plastic covering. An F connector is attached to each end of the coaxial cable. Make sure that the center conductor does not short out to the ground sheath, as this will blow the receiver's fuse and possibly damage its internal power supply. When screwing an F connector onto mating connectors on the back of the receiver, or LNB, you should take care to avoid bending or breaking the cable's inner conductor, thereby shorting out the connection. The receiver should be unplugged before making any coaxial connections to avoid shorting out the receiver's power supply. Once you are satisfied with the total system operation, you will need to go back and waterproof the F connection at the LNB. This can be done by wrapping the connection with a sticky waterproof compound such as coax seal. The type of cable commonly used in satellite TV installations has a characteristic impedance rating of 75 ohms. There are several different kinds of 75 ohm coaxial cable. RG59U coax can be used to span distances of up to 100 feet. For longer lengths, lower loss RG6 or RG11 should be used. To span distances of several hundred feet, special UHF line amplifiers with 10 to 20 dB of gain also may be necessary to compensate for the high amount of signal loss or attenuation. These line amplifiers receive their power from the center conductor of the coaxial cable, just like the LNB does. Above-ground pedestals are available to protect the amplifier from the environment and permit easy servicing should the amplifier ever malfunction. The Feedhorn cable is comprised of 3 color-coded 22-gauge stranded wires. The 3 wires provide power, pulse, and ground connections for the Feedhorn. Each of these wires connect to corresponding terminals on the back of the receiver. The wires are color-coded to help identify them when connecting to the 3 servo motor wires at the feed, usually red for power, white for pulse, and black for ground. The receiver uses pulses to keep track of the position of the Feedhorn's pickup probe. You therefore can adjust or skew the position of the probe and program the optimum polarization for any given satellite transponder into the receiver's internal memory circuit. The Feedhorn's servo motor rotates the pickup probe, which swings back and forth while switching between the horizontally and vertically polarized transponders. Some satellites use an alternate form of polarization known as circular polarization, where the incoming wavefront rotates in either a clockwise or a counterclockwise direction. To receive these signals, a special Feedhorn is required. Keep in mind that there are limits to the pickup probe's clockwise and counterclockwise movements. The Feedhorn must be aligned on the antenna so that the probe can swing the 90 degrees from horizontal to vertical without reaching the limits of travel. If you find that you cannot skew the probe beyond a good picture on all channels, you will need to loosen the clamp that holds the feed onto its support and physically rotate the Feedhorn until it is possible to do so. In extremely cold climates, where a servo motor may freeze up during the winter months, an alternate polarization device called a ferrite feed may be used instead. The ferrite feed, which electromagnetically rotates the polarization of the incoming satellite signal, requires a 2-wire connection. Consult the receiver manual to determine the recommended way to connect the ferrite feed to the receiver. The direct burial cable's actuator line is comprised of 5 stranded wires. These actuator wires should be connected to the appropriate terminals on the mount's motorized actuator and the back of the receiver. Like the Feedhorn servo motor wires, the 3 shielded motor sensor wires also provide power, pulse, and ground. Reed and Hall effect sensors will only require 2 wires, one for pulse and the other for ground. The 2 large stranded wires connect to the large wire terminals at the actuator motor and to the motor wire 1 and 2 terminals on the back of the receiver. These connections supply 24 to 36 volts DC to the antenna actuator's DC motor. Okay, now we're hooked up, so let's try to move the dish to the east or west. If the dish moves in the direction opposite to the one intended, reverse the wires connected to these 2 terminals. The polar mount enables the reflector's direction of focus to sweep across the entire satellite arc by means of a force produced by a single motor called the actuator. But to make this work, 4 separate adjustments have to be made with a high degree of precision. First and foremost, the mount's supporting structure has to be perfectly plumb. Moreover, the main axis of the mount, this part right here, has to be perfectly aligned with the site's true north-south line. This is determined by using a correction factor to compensate for the amount of magnetic deviation that is encountered at the site. The third step is to set this axis to an angle that corresponds with the site's local latitude. The angle of the main axis is called the inclination, with straight up being 0 degrees and the local horizon being 90 degrees. So always remember that you have to tilt the antenna down until you reach the angle required for your local latitude. Some charts may give this angle as the elevation, which is the complement of the inclination. You can subtract the elevation angle from 90 degrees to get the correct inclination angle. Last but not least is the mount's declination setting, which tilts the antenna downward in the direction of the local horizon. On this particular mount, the declination setting is made by adjusting these two bolts right here. Readily available charts and computer programs can supply the specific mount angles that will be required at the site's local latitude. Here in southeastern Ohio, the main axis of the mount has to be set to an angle of about 39.5 degrees. And the declination adjustment adds about 5.5 degrees to that. Even after you've made all of the adjustments correctly, it won't be time yet to snug down all the bolts. That's because of the accuracy limitations of the tools in use. You may have to make some fine-tuning adjustments later on to get everything just right. But once you do have all of these adjustments correctly set, the antenna will track the entire satellite arc with geometric perfection. The first step in aligning your satellite dish is to set the east and west limits. This is referring to the limits of travel for the actuator arm or horizon-to-horizon drive. Although the motor may have physical limit switches to prevent damage to the dish, it is best to set the receiver's programmable limits at positions before the motorized mount reaches its physical limits. Next, adjust the antenna drive until the dish is looking at the highest point in the sky, called the arc zenith. Set the inclinometer onto the polar axis of the dish and adjust the polar axis of the mount to the correct angle for the site location. Declination is the offset angle between the polar axis of the mount and the rim of the dish, which permits the antenna to precisely track the available geostationary satellites. The declination angle at any site is determined by the latitude at that location. The declination setting must be adjusted to the figure for your specific site. You can find out the approximate value by using a chart or computer program. Correct tracking of the total geostationary satellite arc is only possible when the declination has been properly set. Too much declination loses the medium elevation satellites, while too little declination will cause the loss of the low elevation satellites. Set the inclinometer on the back plate of the antenna. Using the declination adjustments on the mount, set the antenna for an elevation angle that is equal to the polar axis angle plus the number of degrees of declination for the site. When moving the dish to the east or west, the dish's look angle should now follow a curve similar to that of the geostationary satellite arc. Determine the elevation of the lowest satellite available from your location and move the dish until the inclinometer registers that angle. Inclinometer readings for the satellite look angles, that is, the elevations of the satellites available in your area, should be taken on the back plate of the antenna or on a surface that is parallel to the plane of the antenna's rim. Set the receiver to a known channel frequency, which should have programming on it. Push the dish to the right or left so that it rotates on the pole until a flash of video appears on your TV screen. If you don't receive any signal at first, or if reception is very weak, fine-tune the Feedhorn skew to optimize reception. Most receivers have a signal level indicator, which often is part of the on-screen graphic menu. The signal strength indicator provides a better reading of peak satellite performance in contrast to just viewing the picture on the TV screen. Push the dish right and left on the pole and move the drive east and west in slight increments until you are satisfied that you have locked onto the strongest signal. Then tighten the mount's bolts onto the pole so that the dish won't rotate. But don't tighten them down totally just yet. Note the numerical reading provided on the receiver's front panel or on-screen display that corresponds to dish position at this location. This is a relative number that changes as the dish moves. Move the dish east or west until you reach arc zenith for your location. Select an active transponder on the satellite closest to the east or west of arc zenith. Now move the dish in the direction of that satellite. If all the settings have been done right, you should have no problem finding it. For peak reception of satellites that are in the upper section of the geostationary arc, adjust the elevation bracket up slightly and then jog the motor drive east and west. If reception is worse, try going down slightly, then jog the motor drive east and west again. You should not have to move the elevation setting very much because you already have preset it for your location. The rule of thumb here is rotate the dish on the pole and use the motor drive to receive the lower satellites, and adjust the elevation of the dish and use the drive to receive the upper satellites, and not vice versa. Fine-tune your tracking by repeating the previous 6 steps until the satellites in both the upper and lower sections of the geostationary arc attain maximum signal strength. If this can't be done, you probably have miscalculated the required elevation or declination settings for the site location. Once you have the dish tracking properly, firmly snug the bolts that secure the mount onto the pipe. Placing a bolt all the way through the pipe may be desirable in high wind areas. Also mark the position of the mount on the pole for later reference. In many parts of the world, dual-band satellite TV installations provide the best of the C and KU band worlds. Special dual-band feed horns are available that place both the C and KU band feed openings at the focus of the dish. You can install an electronic switch out at the antenna which will connect the main coaxial cable to either a C or KU band LNB. The receiver supplies the switching voltage up the center conductor of the coaxial cable. Universal KU band LNBs also are available that switch internally between the 10.7 to 11.7 GHz and the 11.7 to 12.75 GHz frequency spectrums. The dual band feed is a technical compromise that sacrifices a small amount of C-band signal in order to place both the C and KU band feed openings at the focus of the dish. For those situations where the installer cannot afford to sacrifice any C-band signal, a second KU band feed in LNB can be attached to one side of the C-band feed, along the plane of the dish that is perpendicular to the polar mount axis. However, the separation between the C and KU band feed openings inflicts losses and also complicates the installation process. With this shotgun feed, an attempt has actually been made to position the two feed openings even closer together. Another option is to install a second, smaller aperture KU band dish that is permanently pointed at a single satellite, or satellites co-located at a single orbital position. The best way to align a dual band antenna mount is to get the dish tracking on KU band first, receiving all available 12 GHz birds, even those that are only carrying voice and data traffic. The spectrum analyzer is really the best way to get a view into what's going on. Once you've got the dish tracking on KU band, the C-band bird should also pop into view. The adjustment of the declination offset angle is also far more critical at KU band frequencies and should be properly set for adequate tracking of all 12 GHz birds. Most small KU band dishes are offset-fed antennas which position the feed horn away from the center of the dish so that it doesn't block any of the incoming signal. These asymmetrical dishes actually use an oval-shaped subsection of the same parabolic curve that their larger prime focus counterparts use. Another advantage is that the offset feed horn looks up at the cold noise temperature of the sky rather than down at the hot noise temperature of the earth. Offset-fed antennas use a different type of feed horn than their prime focus counterparts. This special feed, which is often supplied together with the dish, is designed to effectively illuminate the oval shape of the offset-fed antenna. Most small dish systems these days provide a combination of feed and L&B called an LNF. Many of these units are designed to switch polarizations by means of a DC voltage which the receiver sends up the coaxial cable. This simplifies the hookup between dish and indoor unit by limiting connections to a single coaxial cable. Simply hand-rotate the LNF to peak one polarization, and the switching voltage will automatically reset the feed to the opposite sense of polarization. Offset-fed antennas usually come with a feed horn support bracket that automatically sets the focal distance between the dish and the feed horn opening. There will, however, be some room for fine-tuning the distance, usually about 1/8 of an inch in or out. You should manually make this adjustment while monitoring the signal with a tuning meter or spectrum analyzer to ensure that you have reached peak level. The satellite elevation coordinates supplied by computer programs, manuals, and other reference materials are almost always for prime focus antennas. When adjusting the elevation angle of an offset dish, subtract the manufacturer's offset angle from the elevation angle provided by your reference. Many offset dish manufacturers supply a gauge on the antenna mount that automatically makes this correction for you. If not, place the inclinometer onto any section of the mount that is parallel with the rim of the dish. In this case, don't forget to subtract the antenna's offset angle from your readings. The fixed antenna mount that comes with the offset antenna usually offers a variety of installation options: on the ground, up a pole, attached to an outside wall, or under the eave of a house. Rooftop mounts are available that either penetrate the roof and attach to the building's rafters, or mount directly on a flat roof or peak. Above all, select the type of mount which will give the antenna a clear, unobstructed view of the satellite. The offset dish most often is used to receive a digitally compressed bouquet of TV and audio services. With a conventional analog TV signal, you can readily see the differences in picture quality which occur while you are tweaking the dish alignment. But with digital, you either get a perfect picture or no picture at all. To verify that you have obtained the highest possible signal level, you will need to use a signal tuning meter. On my right is an analog satellite TV service, and on my left, a digital satellite TV service. Both of these channels are carried on the AsiaSat 2 satellite. Today we're going to see how digital stacks up against analog satellite TV. Under poor signal receiving conditions, an analog TV signal is still visible, but the video is marred by sparklies, impulse noise, which appears as comet-tailed dots of noise in the TV picture. With a digital satellite signal, however, we either have a perfect picture or we have no picture at all. The receiver holds the last frame of video in its buffer circuit and displays it on the screen while it looks for additional data for subsequent frames of video. Once we have sufficient signal to drive the receiver again, video reappears on the screen. Rain, fog, snow, or even rain-filled clouds rolling overhead can reduce the intensity of any Ku-band satellite signal. If you tune a digital satellite TV system just by watching the TV screen, you can obtain a crystal clear picture at the time of install, but the customer may experience a signal outage as soon as the rain begins to fall. Peaking the signal reception to the max ensures that the customer has sufficient signal margin to overcome all but the highest rainfall rates. Annual rain rates vary widely from region to region. Make sure that the customer is aware that some outages will occur, especially in tropical and semi-tropical climates. For example, if a service operator guarantees a signal availability of 99.7%, tell customers that service will be interrupted for about 26 hours each year on average. C-band and S-band satellite receiving systems are not affected by rain fades. In arid climates such as the Middle East, however, all satellite frequency bands are subject to signal attenuation problems caused by sandstorms. Many digital receiver manufacturers incorporate an audible tuning meter into their products. You can turn up the volume of the TV set and then go outside to make adjustments to the dish. Peak signal acquisition occurs when the tone rises to its highest level. Just remember to verify that you are receiving the right satellite before calling it a day. Manufacturers of digital IRDs typically set up default values at the factory for the frequency, polarization, symbol rate, and forward error correction rate of a single digital DTH bouquet. To receive a bouquet which uses different settings, new values must be programmed into the IRD. What's more, the IRD must be fully compatible with the conditional access format which the service provider uses to control subscription authorization. Digital DTH services use a form of modulation called QPSK, short for quaternary phase shift keying. With QPSK, two data bits are combined to produce a representative symbol which is expressed as one of four distinct states or phases. This phase shift typically occurs at rates of millions of symbols or megasymbols per second. Symbol rates may vary widely from one digital DTH service to the next. It is important that the digital IRD be able to tune through the entire range of symbol rates that correspond to the various services which the customer wishes to receive. The FEC rate is the ratio of K bits entering the digital encoder to N bits exiting the encoder. FEC rates of 1 to 2, 2 to 3, 3 to 4, 5 to 6, and 7 to 8 are now in use worldwide. The uplink encoder inserts error-correcting bits into the original signal's bit stream. The IRD uses this extra information to detect and compensate for signaling errors which may occur in the link between program source and destination. With some digital IRDs, the LNB local oscillator frequency must be entered into the unit's setup menu along with the bouquet's default transponder frequency. To switch between digital DTH bouquets on the same satellite, enter the new transponder frequency and polarization, change symbol rates, and switch to the new FEC setting. Keep in mind that it will take a few seconds for the IRD to load the new data. You can select the manufacturer's default settings to go back to the original bouquet. Small dish systems also can be installed to receive free-to-air TV and radio programs, which are transmitted in the clear on regular satellites. And because they're unencrypted, anybody can receive them with one of these free-to-air digital satellite receivers. If the dish owner's intention is to receive free-to-air services from a single satellite, then the installer can use the same antenna installation procedure previously described for fixed DBS antennas. Commercial KU-band antennas like this one have mounts that allow for a high degree of precision adjustment. With commercial grade KU-band products, a lot of money goes into the mount to allow for very fine adjustments in the antenna's elevation and its azimuth, so that you can get onto the satellite with pinpoint accuracy. The cheaper mounts for consumer applications are not nearly so precise. You can see right here that it's just a bolt adjustment. So it's going to take a little extra patience to get things just right. The same low level of accuracy is also found here, where you have another bolt adjustment in order to set the polar axis angle. If you adjust this, it goes in bigger increments than you'd like to have. But that's the way it is with low-cost gear. But if you want to install a system to receive free-to-air programming from multiple satellites, you're going to need a motor for the dish, and that's going to make the installation a tad more complicated. Movable free-to-air antennas use a type of motor that is compatible with DISEC, an international coding standard that sends the control signals for the motor up the same coaxial cable used to send the signals from the LNB to the receiver. And because the power for the motor also comes up the same piece of coax, no additional wiring is required. The mount's polar axis must be precisely aligned to the site's true north-south line, with the polar axis and the declination setting adjusted to the values corresponding to the site's location, just like the big dish system shown earlier. This type of reflector is called an offset-fed antenna because it positions the Feedhorn in the LNB away from the center of the dish. However, the offset angle of this type of antenna must be accounted for when setting the elevation and declination angles of the antenna mount. Additional procedures are also required to tune the free-to-air receiver to the specific transmission mode of each service or group of services sharing the same parameters.
And the channels are changing all the time, and the number one question we get from consumers is, how do I find these new channels if it's not published anywhere? Well, we actually have the solution built right into this remote, where we have a power scan option, and what a consumer can do is actually just go to the remote and press the power scan button, and it brings up the power scan menu. From the power scan menu, if they don't understand what all these parameters means, they can just ignore it and press OK and launch right into scanning that satellite. However, if they do understand what the parameters mean, they can narrow that search down considerably. For example, they can choose which satellite they're going to be searching. They can then choose the polarity, where they can choose all the horizontal transponders, all the vertical transponders, or select all and choose all the transponders. If they're looking for a specific channel and they have some information that it might exist in a certain frequency, they can actually specify that frequency and narrow their search down considerably, which saves them time.
Right.
If they don't know, they can scan the entire satellite for the entire frequency range that their LMB supports by putting in that information here. Typically, it takes about 12 minutes to scan an entire satellite. You can also choose the steps, the frequency steps of doing that scan. In this case, the default is 6 megahertz.
Right.
For a faster scan, you can increase that to 8 megahertz. Or if you want to invest a little bit more time but get a little more accuracy, you can knock it down to 4 megahertz. You can also choose, are you going to scan everything, or are you just looking for the free-to-air channels?
Right.
The locking speed is really important, because a lot of transponders, for temporary transponders, the symbol rate might be very, very low. So for a low symbol rate, you need to spend a little bit more time trying to lock in on that channel.
Yes.
So here you need to do a detailed scan. If you're dealing with higher symbol rate channels, you can just do a quick scan. It'll find it very, very fast and take a 12-minute search down to as quick as about 4.5 minutes.
I notice you don't have FEC on your list. Why isn't FEC one of the choices?
Well, FEC is not necessary anymore, because you can actually scan those satellites and the FEC will be detected automatically. Once you've put in all your parameters, you just press the OK button, and what the receiver will do is it'll automatically start searching that entire satellite throughout the entire frequency range. And for every transponder that it finds, it will just list it up here in the menu. Once it's scanned the entire satellite and has found every active transponder, both horizontal and vertical, it will then go down and download any channels that exist on that satellite. It will continue to search the satellite in 6 megahertz increments, because that's what I specified, and it will continue until it's done the entire satellite. If I go and say, okay, I found the transponder I want it, I can now just hit exit. What it will do is it'll stop right there and start scanning those transponders that it already found. And then it will add these channels to the end of your channel list of all the existing channels that are already in the receiver.
In the good old days of C-band satellite TV, an installer could use a plain old TV set in order to peak the signal, because he could see little changes in signal intensity right on the TV screen. But with digital satellite TV, it's like a light switch. It's either on or off, and therefore we have to use a different method in order to receive digital satellite TV signals. The next step is to program the system to receive 3 satellite TV channels. One on the satellite that's highest in the sky with respect to the site location, a second at the lowest part of the arc that we wish to receive, and a third in between the two. To accomplish this task, we need to have the latest information about each satellite TV channel's frequency, polarization, and symbol rate, the transmission rate in megasymbols per second at which the compressed video signal is being transmitted. Here in southeast Ohio, we have programmed in the parameters for the Ohio News Network on the SBS 6 satellite at 74 degrees west, Al Jazeera on Galaxy 25 at 97 degrees west, and a TV newsfeed channel on Anik F1 at 107 degrees west. Move the dish in small increments from east to west and back again until the TV channel on the highest satellite is located. Then repeat the operation by moving the dish to receive the TV channels on the lowest and midpoint satellites. Once we're receiving the high, low, and midpoint satellites successfully, all the other satellites in between will automatically fall into line. If not, then we'll have to go back and retune the positions for each of the 3 points. If the channels on all 3 satellites are still not coming in, then we will need to recheck the mount's 3 primary settings. For example, you can fine-tune the mount's declination setting to incrementally add or subtract a fraction of a degree from the previous setting. As we have already seen, having too much declination will allow the dish to receive the high and low point satellites, but not the middle point of the arc. Too little declination and the dish will receive the high and midpoint satellites, but not the lowest one. Also check to ensure that the signal from the highest satellite has been peaked. Once we've found a single TV channel on any satellite, then we can use the satellite scan feature to find all of the other digital TV channels on that satellite. A high degree of antenna pointing accuracy is essential when aligning any Ku-band dish, because the reflector's focused view of the sky, or beam, is very narrow at Ku-band frequencies. As a matter of fact, adjustments of as little as 1/16 of an inch can make the difference between a perfect picture and one that is problematic. Antenna pointing accuracy also is essential to minimize the reception of satellites next door to the one we want. For example, because the beam width of a 2.4 meter dish is extremely narrow, it can reject signals from adjacent Ku-band satellites that are only 2 degrees to either side of the antenna's main beam. But as the dish size shrinks to 1.2 meters and then to 60 centimeters, the width of the antenna's main beam broadens. As a matter of fact, the main beam of a 30 centimeter dish is so broad that any satellites just 2 degrees away from the one we want will also be received by the antenna, together with the desired TV signal. This is not a problem with DBS installations because the satellites are spaced 9 degrees apart. However, it can be a problem when receiving free-to-air services on satellites in a 2-degree spacing environment. Professional installers can maximize antenna pointing accuracy by using a precision measurement device such as a signal meter.
I'll show you our Super Buddy meter, our newest release of satellite meters, and it's used primarily for verifying the signal level and the signal quality of satellite signal delivery. It has the major service provider signals stored inside, being DirecTV or Dish Network, as well as the generic KU and C-band satellites. With this particular antenna, we have the ability, using the Super Buddy, to power the different LNBs, and right now my display is showing that we pushed our LNB button and we're powering the 101 LNB. And our meter shows that we've got a signal level of about minus 44 dBm signal strength. And our right bar graph and value shows that we have a signal quality of about 15.3 dB carrier to noise, which is a very good signal quality. These measurements can be taken anywhere throughout the cable network used for the delivery of the satellite signal. In addition to the signal level and quality, we have some troubleshooting features. If you enter our menu button, you can go to the VI screen, and the meter's display shows you the amperage that the LNB is drawing. In this case, it's drawing about 104 milliamps. And if we were connected to a receiver into the bottom port of the meter, it displays the voltage that it's measuring from the receiver, so you can use that for troubleshooting the receiver. In addition to doing DirecTV, Dish Network, and the generic KU band satellites, it also works very well with Wild Blue. It's able to obtain a signal lock on their signals, which is very useful for optimizing the new Wild Blue 1 and the older Anik satellites.
Special dissect switches are also available that will allow you to connect multiple receivers to the same LNB or multiple LNBs to the same receiver.
It was a standard created by Eutelsat in Europe to allow more complex delivery methods in the European Union. But a lot of other countries have adopted the standard or parts of it for their own use. The way that works is that a binary number is encoded onto a 22 kilohertz tone, which is sent by the receiver to the multi-switch. The multi-switch then extrapolates that code to determine which of the three inputs that particular receiver requires to be looking at or requires feeds from. So for each one of the receiver ports, a dissect command is being sent to the switch, and the switch in turn reads that command and connects one of the three inputs to each receiver. So it's independent control for any receiver to connect to any port.
The dissect switch allows 2 or more low noise feeds on multi-feed dishes to connect to the same free-to-air receiver.
It's for FTA dishes, for people who want free-to-air satellite channels. Instead of people, for example, he's from, let's say, from Portugal, he wants AMC4, but he's also interested in another culture, another ethnic program, which is in 97. So instead of having 2 90-centimeter dish on the roof, which is too big for one house, instead of having 2 satellites or 3 satellites, he can just have 1. This is a dish made by FTA Technology. It's 36-inch long axis. This is very simple. It works with FTA dishes, FTA satellites. So you have to point your center satellites, let's say here, for example, on 97 west, the first satellites. So you put your 97 on the 0 degrees, you adjust your dish, then, for example, you want AMC4, which is in 101. So you go 4 degrees between 97 and 101. right here. So you put your LNB right here. Then what you do is just skew the dish to the right angle. You will have 97 and 101 together. It's very simple, very easy. And you can do it with many satellites. You have up to 5. So you can put...
How many degrees of the arc of the sky can you see?
Yeah, the arc is about 43 degrees.
43 degrees.
So if you can start at 97, you can go up to 43 degrees to your left and to your right. And the beauty of this dish, you can have many satellites on the same time, and you just have to put the LNB on the right angle. And then when you skew it, you have all the satellites lined up perfectly. So you don't have to play around with any numbers, you don't have to play around with any elevation or anything. You just put one dish and all the rest will follow.
Another innovative technology coming our way is the high-definition receiver for free-to-air satellite TV applications.
And obviously everyone understands that HD is going to become more and more popular and that there will be more channels in the future.
Two-way satellite systems are also available for enabling rural households to obtain a broadband internet connection. The latest high-speed consumer terminals feature an offset-fed dish with a feed assembly that, on the transmit side, integrates an L-band to KU-band up converter and a high-power amplifier. On the receive side, the feed assembly features the requisite KU-band LNB for delivering incoming signals to one or more PCs located within the home. Transmit and receive signals are combined in the feed assembly's multiplexer, which is located directly behind the Feedhorn. Installing a two-way broadband terminal requires the same steps to be followed as is the case when installing TV receive-only systems. Adjustments in azimuth, elevation, antenna skew, and feedhorn polarization must be correctly made in order to acquire and peak the signals coming from and going to the desired satellite. We can use this chart to find out the correct skew angle for the back of the antenna for the site's latitude and longitude. Here in the center of the U.S., the skew angle is only 88 degrees. It's not that much of an adjustment in order to set the dish.
With an oval-shaped dish, it is important that the reflector tilts to the right or left of the mount's main axis to account for the degrees of difference between local longitude and the longitude of the satellite. When an oval-shaped dish is mounted onto the polar mount, this adjustment happens automatically as the antenna moves from one satellite to the next. But with an as-L mount, the skew angle has to be set manually to compensate for the difference between local longitude and the longitude of the desired satellite.
In other parts of the country, the skew angle is likely to be great. But here in the central part of the USA, a slight adjustment from 90 to 88 is all that's required. One major difference with a two-way satellite system has to do with the feed, which is designed to illuminate the unique shape of the entire antenna, an oval.
Other differences are encountered when connecting the two-way broadband terminal's indoor unit to a PC. Fortunately, some of today's broadband satellite terminals feature indoor units that are compatible with the same plug-and-play DOCSIS standard upon which cable modems and other high-speed devices for connecting to the internet are based. Mobile satellite TV terminals, and even those for enabling a broadband internet connection, are now available. Some of these terminals are so smart, in fact, that they can install themselves with a minimum of muss and fuss.
Inside here it's got auto tilt sensors, it's also got a compass, and it's also got a GPS locator. So before it even starts to look, it has a general idea of where the satellite is. Once we press the go button, it's designed just to be for drivers of the trucks. He presses acquire, the satellite knows where to look when he reaches there. It does a small search pattern and it acquires within 2.5 minutes.
The spectrum analyzer is the single most powerful tool available to the professional satellite installer. It is a specialized receiver that continuously sweeps across an entire band of frequencies and presents the output as a video display of signal amplitude against frequency. The result is a panoramic view of the amplitudes and frequencies of all the signals present in the band of interest. Because of the switch to digital, having access to clear analog TV signals is becoming less and less likely of a proposition each and every day. The professional installer can use a spectrum analyzer to track digital satellite TV signals right across the entire geostationary satellite arc. This portable battery-operated spectrum analyzer displays signal amplitude from left to right and ascending frequencies from bottom to top. As we move the dish through the satellite arc, we can easily detect and peak the settings for each and every available satellite. By adjusting the analyzer's frequency marker, we can display the center frequency for any one signal on the analyzer's digital readout. We can also adjust the bandwidth of the spectrum analyzer to look at an entire satellite frequency band or at just one satellite signal. The shape of the signal on the analyzer's display also gives us clues as to the nature of the transmission taking place. Conventional analog satellite TV signals have one kind of characteristic shape, while digital signals, including compressed digital video, have another. The spectrum analyzer is also the best tool for adjusting the separation between opposite senses of polarization. Here, we can see several strong carriers with a few weaker ones sticking up from the noise floor to screen left. As we make adjustments to the feed's polarization settings, we can visually verify that any unwanted cross-polarized signals have been nulled out. We can also measure the side lobe performance of the dish, which will give us some indication of antenna surface accuracy and feedhorn positioning. All antennas generate side lobes, which can amplify signals that are several degrees to either side of the antenna's main beam. The gain of these side lobes must be 12 to 15 dB down from the main beam to prevent adjacent satellite signals from causing interference. The spectrum analyzer reveals the amount of side lobe rejection, as well as how far off axis these side lobes actually are. A spectrum analyzer can even be used to measure the carrier-to-noise ratio of the satellite antenna system. This C/N value represents the difference in dB between the peak carrier here and the average noise level hiding under the signal. To do this, we first measure the carrier peak and then jog the antenna away from the satellite until we can measure only the noise floor. We must also make one mathematical correction to our numbers, which factors in the bandwidth of the satellite signal, as well as the bandwidth filter of the spectrum analyzer itself. Let's try a quick measurement. This carrier has an amplitude of -54 dB, while the noise floor below it is -72 dB. The correction factor is equal to the satellite transponder bandwidth divided by the spectrum analyzer filter bandwidth times 1.5. If the satellite transponder bandwidth is 36 megahertz and the analyzer bandwidth is 8 megahertz, then the correction factor would be 36 divided by 8 times 1.5, or 6.75. The actual noise equals our noise floor measurement plus the correction factor of 6.75. The carrier to noise is the carrier minus the actual noise. In this case, C over N would be 11.25 dB. With this DVD, you have bought a ticket to a destination from where you can contribute to both the technology and its beneficial effects. And with a little practice, soon you'll be putting up satellite systems like this. For Shelburne Films, this is Mark Long.